Okay. So I'm glad you all are engaged. Some of you are asking advanced questions. We may not be able to answer all of them in this course. But now we know the reorder buffer. Keep that in mind. Reorder buffer is good for preserving sequential semantics. That's one function. But we just saw the other function. It's actually able to rename the registers. So we're going to take advantage of that renaming functionality. Okay, so now we're starting the out-of-order execution lecture. This is a fascinating topic. People have worked on it for a long time. The fundamental concept is developed in 1960s, actually. I'm going to give you a history of it also. So this is where we are, basically. We're done, essentially, with at least some issues in pipelining. We haven't covered. There are a lot more issues. If you take an advanced course, if you design your own pipeline, you will figure that out. Now we're going to do out-of-order execution. And then we're going to switch to other execution paradigms. Okay, I've already given you this one. Maybe let me actually talk a little bit about this based on the questions that I received very quickly. So whenever you're decoding an instruction, you do multiple things. You first access your source registers, right? You need to get your source registers. And your source register can be in the register file, based on the picture we drew, can be in the reorder buffer, or can be in the bypass paths. So let me actually switch over here again very quickly. We're going to see more of this soon when we talk about out-of-order execution, but I want you to get this very clearly. So let's assume that you're fetching instruction at decoding instruction at R3, R4. What you need to do is first figure out where is R3 and R4. Now, if both of them are valid in the register file, it's easy. You get the value, right? That's it. And then you can execute. If, let's say, one of them is invalid over here, then the value might be coming from here or coming from the bypass paths, right? So how do you figure that out? So basically, let's assume R3 is invalid. Then the latest instruction that wrote to R3 should have put its reorder buffer entry ID over here. So you know that R3 is going to eventually be produced by reorder buffer entry 131. During that decode stage, you check whether that R3 is already there. Now, if this is 1, meaning R3 is valid, already produced by this entry 131, you can get the value from here. Make sense? Now, there may be the case this is also 0, meaning that R3 is going to be produced by 131, but it's not produced yet. Then the instruction that's going to produce it is still executing in the pipeline. There's a pipeline somewhere over here. And you need to wait for it. What does that mean? If you don't have the bypass paths, you stall. If you do have the bypass paths, then you need to be able to schedule the instruction such that it gets the value from the bypass paths. And we saw bypassing forwarding last time, so you should construct that picture. Okay? So now we're going to make use of these concepts to build out-of-order execution. Okay, let me switch back to this. Hopefully it did switch, that's good. So we already built this pipeline. I'm not going to go over this in detail. We just covered this actually. And always recall this data dependence types. We've now eliminated the anti and output dependencies. Now we're making the system look more like data flow actually, at least in the underneath. Because in data flow, what really matters is this, right? Remember, data flow, there's no registers in data flow. If you think about when we discuss data flow, it's all about data flow. You produce some data and there's a consumer of data. This is the only true case. Here, there is no producer-consumer relationship between the instructions. It's just dependence on a name, right? This instruction doesn't consume what this is producing, nor the other way around. They're just connected to each other because they happen to reference the same register. But the value in the register is completely different. It's just the name. As a result, we can eliminate this easily. And what we did with the reorder buffer is eliminating that, renaming. And that's true for this also. There's no data flow relationship between these two instructions. This R3 is actually referring to completely different things. Okay, so that's why we eliminated, and I already talked about this. Essentially, what we've done is we mapped the register ID to a reorder buffer entry ID. Or you can think of this as architectural register ID is mapped to a physical register ID. And after renaming, reorder buffer entry ID is used to refer to the register. That's going to be the name of the register. Okay, so now we're going to build out-of-order execution. So we're still in order in the sense that we're not able to, if there's a true data dependency over here, we're not going to dispatch this instruction. Dispatch means it's the act of sending an instruction to a functional unit. It needs to wait. Okay? But renaming with reorder buffer eliminates stalls due to false dependencies. So if you have false dependencies, you can still keep going. But the problem is that a true data dependency stalls the dispatch of younger instructions. So if you have an instruction over here that's waiting for register 3, and register 3 is not available yet, and you cannot get it from the bypass paths, because the bypass, you still need to wait to be able to bypass, you just wait. Meaning that you just stalled the pipeline. But what if there were some other instructions and later in the program execution order that didn't need that value, or that didn't need any value that's produced by any instruction in the pipeline? That could have gone. Well, too bad. We've stalled the pipeline. They cannot even get into the pipeline, right? So out-of-order execution is going to solve that problem. So the key question is, can we do better? So we're going to look at two pieces of the program. Initially, ignore this question over here. But basically, if you have this code, this add is dependent on this multiply clearly. Multiply produces R3, the add consumes R3. But these younger instructions are completely independent of both of these instructions. So if you have an in-order pipeline, what happens is this add waits for 8 cycles until the multiply produces R3. And these poor guys also wait, even though they didn't have to, because they could have gone, right? So a good compiler, what a good compiler would do is recognize this, that these are independent, and reorder them before the add so that they could execute. That's one way of solving the problem, right? But if this is the code that you have and the machine is executing it, this add needs to stall. And all of the other instructions cannot go into the pipeline. Similarly, that's true for the load. I just changed this to a load over here. And if the load is producing R3, this add stalls. Now the difference is this load can take thousands of cycles, right? So it's difficult for a compiler actually to reorder the code over here. It could reorder, but how are you going to fill thousands of cycles with that if you don't want to stall? So okay, basically the first add stalls the pipeline. These two pieces of the code, that's what they have in common. An add cannot dispatch because it's source registers. I shouldn't say registers. It's just one register over here because we don't know what R1 is. R1 is assumed to be available, is unavailable. As a result, these later independent instructions, the blue ones, cannot get executed, and you lose performance. So, okay, how are the above code portions different? Load latency is variable. I've already given you that. So multiply latency is usually not variable, but it could also be variable. You know, it depends on the value that you have. If one of the operands is 0, you may have a shortcut in hardware that says that directly gives you 0, right? You have a 0 checker. As opposed to doing the multiply cycle by cycle, you just check if any of the operands is 0 and you return a 0. So that could also be variable. And if you want to do the code reordering at compile time, you may not always know the latency. So even multiply latency could be variable, but load latency is a lot more variable because you may hit in the cache, it could be 3 cycles, 1 cycle. You may hit in the next level cache, it could be 40 cycles. You may hit in the next level cache, it may be 80 cycles. And you may miss all levels of cache and have to go to memory. It could be 650 cycles in Xbox 360, if you remember. Okay, so this part is actually, loads are a lot difficult to handle for the compiler. So that's why this point over here. If the compiler is able to reorder the code such that it can eliminate the stalls, that's good. You've seen this in the last lectures, but it's not always able to do this. One of the reasons is it doesn't know the latency of the instructions. And the other reason I will put over here is, what if there was a branch somewhere over here? If there's a branch, if and else, how can you reorder an instruction? This is actually a dilemma that compilers make, because you don't know if the instruction is going to be executed or not. Right? You cannot take this instruction, move it up, because it's under a branch. Okay, think about that. We're not going to go into this, and we're not going to really go into this in this course. But if you take a compiler's course, that's what the compilers do. Figure out how to reorder the code in the presence of all of these difficult issues, like branches, long latency. But it's not easy. In the end, it's not very easy. They actually jump through a lot of hoops that's employed in all compilers that are out there, but they still cannot achieve the performance of what I'm going to describe next, which is the out-of-order execution. Okay, so the problem that we're going to solve is in-order dispatch, in-order scheduling, or in-order execution, it's called. I like in-order dispatch, because you're really dispatching an instruction to an execution unit. So a solution is really out-of-order dispatch. Basically, we want to do out-of-order scheduling. Whenever we get an instruction, whenever we are decoding it, we want to be able to say, okay, you can go out of order, because you have all of your values. And then we're going to fix the problem later on with the reorder buffer. So we don't need to worry about fixing the reordering. We've already solved it. And we've seen the basic idea of out-of-order dispatch before. This is really about data flow. And we're going to use the same principles. We're going to build a mini data flow engine in hardware inside the processor. So data flow says you fire an instruction only when its inputs are ready. And that's what exactly we're going to do. We're going to keep track of the readiness of the source operands of each instruction. And if they're both ready, then the instruction is going to execute and produce a result. And that result will be sent to all of those instructions that are waiting for that result. And all of those instructions will capture that result and will become ready if both of their source operands are ready. And then instructions will execute, and then they will produce a result, and then they will fire, basically. So instructions will be firing their results, and instructions that are waiting for those results will be matching those results. So we'll look at the machinery of this. So we will use basically very similar principles, but not exposed in the ISA. We're going to do everything in a von Neumann architecture. Von Neumann architecture says everything needs to be executed sequentially. We're going to break that completely. We're going to execute everything in data flow order. And then we're going to clean up this mess with the reorder buffer that we've discussed. Okay, so just quickly before we go into it, there are other ways to prevent dispatch stalls. I've already given you actually the compile time, instruction scheduling, and reordering. If you can do it at the compile time, that's good, but there are a lot of limitations related to this. And people have tried a lot, actually, to make compile time reordering match the performance of out-of-order execution. It's not easy. Usually, compile time reordering actually helps a machine, but it's very difficult to match a very good out-of-order execution machine. And you've seen other examples. So whenever you have an instruction, you don't know the value. Let's say it's sourcing register 3. You predict the value. Maybe the R3 is 0, right? I'm not going to go into this. This is actually employed in very limited ways in existing processors, but it's caused a mess in the sense that what if your prediction was wrong? Okay, that's where we will leave it for now. But we've seen something else, which is fine-grained multi-threading, which is do something else, right? So if you remember, fine-grained multi-threading is every cycle you fetch from a different program, a different thread. Assuming there are no data dependencies between those different programs, you have no problem. You never stall for dispatch. Because by definition, you've eliminated the data dependencies, true dependencies, right? Whenever an instruction gets to the dispatch stage, the next instruction is completely independent because it's from a different thread. So that's another solution to the problem. And you've also seen the downside of the solution. If you don't have enough threads, there's a problem. If you have only one thread, and if the performance of a thread matters to you, this is actually very bad for the performance of that thread, because you have this pipeline, but you're really not utilizing it for that particular thread. Every cycle you're fetching from a different thread, and if you want to get rid of the data dependencies, you need to ensure that there are no instructions from that thread that are dependent on each other. So you fetch from a thread every n cycles. If you remember Frank's lecture, you fetch every 8 cycles, for example, from a thread. That's not good. The performance of that latency critical thread didn't improve. It may be very useful for throughput, like GPUs use fine-grained multi-threading, if you remember again. And there you have lots of independent threads, and what you care about is throughput, so you can do this. But if what you care about is latency, when I press this button, I want to get this working, that's a latency-bound program. If a single thread is handling that, fine-grained multi-threading doesn't help you, because you really need to execute the sequence of instructions that need to start when you actually press this. And that latency is important, because otherwise I'll not be happy, because this will take minutes to respond, right? Okay? So there are other ways of solving the problem, but not all, they all have different trade-offs, as you can see. And computer architecture is all about trade-offs, if you remember. It's the soul of architecture. Okay, so we're going to look at out-of-order execution. It's also called dynamic scheduling, not static scheduling. Static schedule is static, it doesn't change. Dynamic scheduling is dynamic, it changes based on the availability of data in this case. So the key idea is, what is the key problem? We have this instruction that cannot move because it's dependent on something else that's not ready yet, some other instruction. So what do? Well, move that instruction out of the way so that independent instructions can go into the pipeline. It's a very simple idea. How many of you drive cars? Okay. If there's a car in front of you that's slow, what do? You take that car and move it out of the way, right? So that's one solution. That's what we're going to do. So basically, you pass the car. That's another solution. If you have space to pass that car, you can do it. Or the car basically says, okay, I'm moving too slowly, so I'm going to move to the next lane over here. Or I have to stop for some reason. I need to wait, so I get out of the highway, right? I get out of the road. That's the idea. So basically, we're going to introduce a place to keep these instructions. We're going to call them reservation stations. For whatever historical reason, people call them reservation stations. You can think of these as rest areas for cars. If you're going through the highway and for some reason you're dependent on something, you basically go out of the highway so that other cars can go. It'd be terrible if every car that's dependent on something had to wait in the highway, right? Makes no sense. Exactly, the pipeline doesn't make no sense. Doesn't make any sense if you're waiting for a dependency and no other instruction can go. So that's the first thing. While the instructions are sitting there in these rest areas or reservation stations, we're going to monitor the source values. Basically check if the source values are ready for this instruction. If they're ready, then we can actually fire this instruction. When all of the source values of an instruction are available or ready, are produced, then we fire or dispatch the instruction. So that's the dispatch. That's out-of-order dispatch. You basically dispatch an instruction when its source values are ready, and that's exactly the soul of data flow. So instructions are now dispatched in data flow order, not control flow order. Instructions are put into the reservation stations in control flow order, but the execution, dispatch into the execution units happens in the data flow order. And the key benefit is now independent instructions can execute and complete in the presence of a long latency operation. If you have a long latency multiply and then an instruction that's dependent on it, you don't wait for that. Other instructions that are independent can go and execute and even finish. So you don't need to stall the pipeline for these long latency operations. Okay, so this is a simple example, a high level first, and then we're going to go into the machinery of this. So this is a machine with in-order dispatch and precise exceptions, and this is the code that we're executing. If you look at the second instruction, it's dependent on this multiply, so it needs to stall. As a result, the blue instructions that are independent of either of these also stall. And then this red one also stalls because there's a true data dependency over here. So if you do the calculations, you get 16 cycles over here. Sounds not too bad. If you do out-of-order dispatch and also have precise exceptions in the end, basically write the results into the reorder buffer, write the results into the register file in program order, this is what you do. The second instruction in the decode stage doesn't stall. It basically goes into these reservation stations and waits. Now you can fetch the next instruction. It also goes into reservation station. It becomes available right away, and it executes. The next instruction after that can also execute. We're filling the pipeline nicely right now because we've moved this dependent instruction out of the way into the reservation stations. And again, if you do the calculations, you get 12 cycles as opposed to 16 cycles. That's significant benefit. You've improved performance by 25%. But this will come at a cost. Okay. And of course, this is just a toy example, right? If you actually look at a lot of dependencies and very long latency instructions, the benefit of out-of-order execution has been shown to be very high compared to in-order execution. Okay, so what do we need to do to enable this? First of all, we need to link the consumer of a value to a producer. An instruction that needs a value should be linked to the producer of that value. We know how to do this with register renaming, so that we can track when the producer produces the value and the consuming instruction needs to fire. So you need to buffer the instructions until they're ready to execute, take them out of the way of independent instructions. Instructions need to keep track of the readiness of their source values, because the instruction is going to go into the functional unit after both source values are ready. And when all source values of an instruction are ready, you need to dispatch the instruction to the functional unit. So we're going to go through an example of this, but these are really the 4 things that you need to enable out-of-order execution. So how do you link the consumer of a value to a producer? That's register renaming. If you remember this register file, I have valid, value, and the reorder buffer entry. Let me call that reorder buffer entry a tag. We rename a register to a tag, and the tag identifies the instruction that's going to produce the value. Okay? So we rename the register, and we're going to use that tag to identify the instruction that's going to produce that value. How do you buffer the instructions? You insert the instruction to reservation stations after renaming. We'll see that. How do you keep track of the readiness of the source values? Basically, when an instruction finishes execution, you know that instruction, you tagged it. If it's going to produce R3, it is a tag. Reorder buffer entry, let's say. We're going to show that that tag could be anything, actually. You broadcast the value, basically send it to everywhere in the machine, and you also broadcast a tag, meaning send that tag to everywhere. And instructions that are waiting for that tag compare the tag that they're waiting for to the tag that's broadcast, that's sent. If there's a match, then they capture the value, because the previous instruction that's producing the value broadcast it, and they're linked to each other with this tag. So we will see this. It'll become a lot more clear when we actually go through the animations. But that's how we link the instructions, and when an instruction finishes, produce the value, that's how you communicate the value to a dependent instruction, because the producer instruction has a tag saying A, for example, and the consumer instruction is waiting for that tag, and there's a matching that happens. Yes?
What happens if this buffer or the reorder buffer gets full?
Let's ignore that for now. If you get full, you stall, basically. We're going to assume that it's not full. But whenever some structure gets full, you stall. Yes?
What's the point of even broadcasting the value itself when the value could actually just be read from the register?
Absolutely, yes. That's a very good point. But you could optimize it. Okay, so when all of the source registers, or source tags of an instruction, source values of an instruction are ready, now you can dispatch the instruction to its functional unit. You can call it as instruction waking up. Instruction is sleeping in the reorder buffer because some of the values are not ready. It's monitoring the source values. When a source value gets produced because somebody broadcast a tag, the instruction wakes up because all source values, all of the source values are produced, and then it gets fired into the execution unit. Of course, if there are multiple instructions that are awake, you need to select one per functional unit. Okay, so that's the idea, basically. It's very simple, right? Now we're going to complicate the machine a lot more. So this, very quickly, a little bit of history. This was invented in 1967 in IBM 36091. This is not the first out-of-order execution algorithm, but it's perhaps a more elegant one. The older out-of-order execution algorithm was actually by Control Data Corporation in the 1960s. It was a different algorithm. But if you're really interested, you can read this paper. So the major difference today, at that time, for some time, for about 20 years or so, this was a good algorithm, but it was very difficult to employ it in practice because people didn't incorporate precise exceptions onto it. So things were getting out of order, and it was difficult to debug. Now, once you add precise exceptions to it, which these papers actually did, these papers heavily influenced Intel's first out-of-order engine, Intel Pentium Pro. If you actually read the book Pentium Chronicles, it's a beautiful book that I would recommend. It's about business, it's about technical, how do you actually design a out-of-order machine. It talks about that by Bob Colwell, who was the chief architect of Intel Pentium Pro. You will see the history of it. Essentially, the reason out-of-order execution became everywhere is because of what we just discussed earlier, a reorder buffer, or a mechanism to ensure that instructions are reordered at the end to the sequential processing. And basically, it's used in all high-performance processors. So this is the pipeline that we're going to build. And I call this a pipeline with two humps, if you will. So you have an in-order engine. You decode the instructions in order, rename them, and put them into reservation stations. And instructions basically wake up over here. They get scheduled into the execution units. And whenever an instruction finishes, it broadcasts its tag and value to wake up instructions that are waiting for it. And instruction also goes into the reorder buffer at the end. And then an instruction finishes, updates the architectural register file after that reorder buffer, whenever it becomes the oldest. So this part we've already covered. This part we've already covered. Now we're going to look at this part. So this part of the pipeline is really completely out of order now, the scheduling. So the first one is reservation stations. It's also called the scheduling window. And the second one is reordering. So you have a reorder buffer, instruction window, or active window. Maybe this is a good analogy of pipeline with two humps, right? It's not an exact analogy, but basically instructions come here, and then they get reordered in the middle, and then they go out. Okay, that's a joke. But essentially, you have these two big things that are reordering the flow. Here it's in order, here it's out of order, here it's in order back again. Okay. And this is from the paper that you're supposed to read, which is really still one of the state-of-the-art surveys of how existing out-of-order execution machines behave. So we're going to see this. I'm going to skip this. You can read this. And this is from 1965 when Tomasulo designed his machine, the first out-of-order machine. Okay, so recall the register renaming. So we're going to rename things. So we're going to use the register file that we developed, actually. This is also called the register rename table now. Register alias table, except things are a little bit in different order over here. We're going to fix that in a little bit. Basically, a register can be valid. If it's valid, you get the value out of the register alias table or register file. If it's invalid, it's going to be produced by the instruction that has a tag. And that tag is some other namespace, basically. Remember, we associate that tag to a reorder buffer entry, but it could really be anything. As long as you identify the instruction, it uniquely identifies the instruction that's going to produce that version of that register. So it just needs to be a unique name. Okay. So very quickly, Tomasulo's algorithm. So basically, whenever we are decoding an instruction, we check if there's a reservation station available before renaming. If there is no reservation station available to put this instruction, we stall. That answers your question. So whenever you run out of entries to put the instructions, you need to stall. And instruction and renamed operands are inserted into the reservation station if one is available, and you only rename if reservation station available. While in the reservation station, each instruction watches the common data bus to capture the tag, and when the tag is seen, you grab the value for the source and keep it in the reservation station. When both operands are available, instruction is ready to be dispatched. And when the instruction is ready, you dispatch it to the functional unit. And after the instruction finishes in the functional unit, you basically broadcast the tag and the value. And register file is also connected. Register alias table is also connected to this common data bus. And we already discussed the register file. Okay, so now let's go through an example of how this works. We're going to execute this program, basically. This is fetch, decode, execute, write back. We're going to assume add is 4 cycles, multiply is 6 cycles. We're going to assume 1 adder and 1 multiplier. So there are questions. These are actually good exam questions also. How many cycles does it take to execute this program in a non-pipeline machine, an in-order dispatch pipeline machine with imprecise exceptions, no forwarding and full forwarding? There are 2 examples of it. And in-order dispatch pipeline machine, an out-of-order dispatch pipeline machine with imprecise exceptions. So ignore the reorder buffer for now. So this is the same question. And I'm not going to do the first part. This is the execution timeline with scoreboarding. It looks terrible. It takes about 31 cycles. This is the execution timeline with data forwarding. You can reduce the execution time to 25 cycles. Okay, you can do this on your own. We've already done it. And if you actually have Tomasulo's algorithm, which is out-of-order execution, you actually reduce it to 20 cycles. So your 25 cycles become 20 cycles. Now let's take a look at how we make it 20 cycles. So in the past, I used to draw this by hand, but one of your colleagues who took this course about 2 years ago was nice enough to actually provide animations for what I used to draw by hand. So we're going to use the animations now. So and this is the animation beginning. Okay. So this is the program we're going to simulate. It's the same program that I showed you, multiplies and adds. This is the initial value of the register alias table. So you have all registers that are valid, and these are the values. So tags don't matter, because everything is valid. And this is the reservation station for the add unit, and this is the reservation station for the multiply unit. And each unit has an adder and a multiplier, and whenever an instruction finishes, it produces a tag, and it produces a value that gets broadcast everywhere. And let's simulate this program first. Before that, we already said add and multiply execution units have separate buses, so they can actually finish at the same time. And initially, reservation stations are all invalid, empty. I'm not showing those invalid bits over here, but there needs to be some mechanism that allocates these reservation stations. And all registers are valid, because that's the beginning of the program. Okay, let's start with cycle 0. This is cycle 0. Nothing has happened yet. That's easy. Cycle 1, we fetch the first instruction. Nothing really interesting happens, because something interesting happens when we decode that instruction, right? So let's take a look at how we decode that instruction. So basically, this is the decode of the multiply instruction. What do we do? First thing is, it needs to be allocated a reservation station entry. Is there a reservation station entry available? And the answer is yes. This is a multiply, so it needs to be allocated somewhere over here. So we're going to allocate it to reservation station X over here on top. Now, what does that mean? We basically check if we already did this. Second step, we need to read the source values and tags from the register alias table. So basically take register 1, index register alias table, get these. So it's valid. As a result, its value is 1. Tag, we don't care. So we're going to put that into the reservation station. The second source is R2. Again, we read it and put it over here. Now, if you see, both of these are valid, so this instruction should be able to execute in the next cycle. And you have the values also in the reservation stations, right? Now we need to do some important step. Now what's happening is, this instruction is writing to register 3. Register 3 is going to be produced by a reservation station tag X. So we need to rename the register so that later instructions that need that register 3 can refer to X. So what does that mean? The register is now invalid because the value in the register file is not up to date anymore, but the value is going to come from tag X, meaning that the instruction that was just allocated to reservation station X is going to produce that value. So that's our tag. Later instructions are going to get that tag if they source R3. Okay, so now R3 is renamed to X, as you can see over here. Its new value will be produced by the reservation station that's identified with tag X. And as you can see, these are all happening concurrently, by the way. Multiply in RSX is ready to execute in the next cycle. Of course, you need to get the source operand before you rename. So if you're writing to the same register as you're reading, you need to first get the old value, and then you update the name, right? Okay, so in the next cycle, multiply in this reservation station entry is ready to execute. Let's take a look at the next cycle then. So there are two things that are happening. Multiply in RS starts executing because there's some logic that checks if both of the sources are valid. If both of them are valid, that's great. We can send it to the execution unit. How do you do that? You check the readiness of both sources. Then the instruction wakes up. There's logic that does that. You can do it in the previous cycle a little bit also, but we're not going to talk about timing for now. And then the instruction gets sent to the multiplier with its source values and the tag. So X, because eventually you need to send the broadcast tag and the value. And it will take 6 cycles. So we can forget about it for now. We also decode the next instruction. Let's take a look at how the next instruction gets decoded. This is an add that's writing to R5. It's reading from R3 and R4. Remember, we're going to go through the same steps. First, we need to allocate a reservation station entry. Is 1 available? This is an add. Yes, it's available. So we're going to allocate reservation station entry A for this. The next step, we're going to rename the source register. No, we're going to read the source registers from the register file. One source register is R3. R3 is not valid. The tag is X. Value, we don't care, because value is not trustworthy over here. It's going to be produced by X. So we're going to read that entry directly into the reservation station so that we can monitor this tag. The next one is R4. The next source register is R4. So R4, oh, sorry. There you go. Okay. So, okay, this is it. Basically, R4 is valid. As a result, its value is also stored over here. Tag, we don't care. Now we need to rename the destination register. That's the next step. Destination register is R5. R5 gets renamed to the reservation station entry that we just allocated this instruction that's going to produce R5. So R5 valid bit becomes 0 and the tag becomes A. Sounds great. Right. Now add in RS, reservation station A, cannot execute in the next cycle because one source is not valid. It's just going to wait there. But the beautiful thing is, in the next cycle, add in RS A waits because its one source is not valid. But we can now decode the next instruction that's independent. It turns out we will see that it's independent, which we couldn't do in an in-order machine. Okay, let's take a look at what we do. We basically do exactly the same thing we did in the previous cycle for decoding. Now you know what to do. We first figure out whether we can allocate a reservation station entry for the add. The answer is yes. Well, we allocate reservation station B to it because A is already occupied. Then we read the source operands. What does that mean? We read R2 and R6. Now if you go read R2, you will find that it's valid. Its value is 2, great. If you read R6, you will also find that it's valid, and its value is 6. So in the next cycle, this should be able to execute. And we also rename the destination register R7 to the reservation station entry ID that we put this instruction into. So R7 gets renamed to B. It's going to be produced by the instruction that we just put into B from now on. Okay. Now we placed an independent instruction into the pipeline without stalling for the previous instruction that had a true dependency. And this new instruction that we placed is ready to execute in the next cycle. And in the same cycle, we're also fetching the next instruction clearly, right? This is a pipeline. Okay, let's take a look at the next cycle. So basically, this instruction will be executed out of order in the next cycle. Next cycle, this multiply is still executing. This add is still waiting in A over here. Now this add can start executing because its source values are both valid. And that's the heart of out-of-order execution. Essentially, we've enabled the execution of this instruction without stalling the pipeline for this instruction that was dependent. And this instruction starts executing out of program order. It's going to take 4 cycles, and you supply the tag and the source values, and it's going to produce the addition of the source values, and when it's done, it's going to broadcast the tag and the value. Okay, now we're going to decode the next instruction in this cycle, and it's the same drill, basically. It's going to get boring. So I'm going to go through it very quickly. Basically, you need to read, first of all, you need to ensure that you can allocate a reservation station entry for this add. We allocate reservation station C. We read the source operand 1, source operand 2. They both happen to be valid. So this instruction is also going to be able to execute in the next cycle. That's good. And then we rename R10 to the reservation station in which we allocated this add into. So R10 becomes named to C. Okay. In the next cycle, this is still executing. The first add is still waiting. The second add is still executing. Now this instruction we previously placed into the reservation station can also execute. That's also going to execute out of order. That's good. The next instruction is going to get renamed. Let's take a look at this a little bit. It needs R7 and R10. It's a multiply. The first step is there a reservation station entry available? It is available. That's great. We're going to read the sources, R7 and R10. They're both not ready, as you can see over here. So we're going to put them into the source 1 and source 2. So this instruction clearly is not going to execute in the next cycle. But it's going to wait for the values that are produced by tag B and tag C, meaning that instructions that are in reservation station B and reservation station C. So by just looking at this picture, you can kind of tell which instructions are dependent on each other, right? The instruction that's placed into reservation station Y is a multiply. It's waiting for its first operand to come from the instruction that's in reservation station B, and the second operand to come from reservation station C. That's how we link the instructions now. You can actually reconstruct reverse engineer the data flow graph by just looking at this picture. And we're going to do that in the beginning of next lecture. But I'll finish this example and then we'll finish this lecture. Okay, so that's good. Now let's go into a more interesting case. So this is cycle 7. This instruction cannot execute, but this instruction we decode, the last instruction, R5, R11. Basically, we allocate a reservation station entry, and this instruction also happens to have both of its sources not ready. It's waiting for tag A and tag Y. Now let's take a look at what happened to R5 here. It's interesting. R5 was named to A before. It was going to be produced by this instruction that's in A, because this instruction was writing to R5. Now there's another instruction that writes to R5. It basically renames R5 to its reservation station tag, D. So now every instruction that comes afterwards is going to get the correct value of R5 from this tag. That's the beauty of renaming. You can link instructions appropriately. Okay, at this point, all 6 instructions are now decoded and renamed. If you actually look at this picture, you should be able to reconstruct the data flow graph. Actually, in this case, you should be able to reconstruct the program. If I don't give you this program, for example, over here, and I give you just this, you can give me the program. Okay, we'll see that. Okay, we discussed what happened to R5. So cycle 8 is an interesting cycle, so we're going to spend a little bit of time on this. This is the first slide, that's why. So what's happening in cycle 8? So multiply in RSX, reservation station X, is done actually, because this is the last cycle. And we're going to send the value out. We're assuming that in the last cycle of execution, you can send the value out in this case through bypass. So what we do is we broadcast multiplies tag. Essentially, this is what's happening. X gets broadcast everywhere to all of the locations where there's a tag. And then all of the locations have comparators. They compare the broadcast tag X to the X that they're waiting. So if you look over here, this location was waiting for X, R3. It was not valid, and was waiting for X. This was not valid, and this was waiting for X. Recall what this is. This is this instruction that is waiting for R3. This is broadcasting R3 now, at least that definition of R3. And nothing else is really waiting for X. So what happens is these locations compare the tag to the broadcast tag. If the tag matches, and if the val bit is 0, that means that they're really waiting for this value. So what they do is they capture the result, which is also broadcast, and become valid. Because they were waiting for that value, and they got it. And as a result, this instruction now can execute because it's source register 1 is valid, and source register 2 is valid. So it's ready to execute in the next cycle. In the next cycle, this is going to go into the adder. Okay, this is the first slide. So we broadcasted the tag and we broadcasted the value. That's a lot of wires. Let me finish this and then we're going to be done. So the second thing that's happening is exactly the same thing. It turns out this instruction add is also done. So it does exactly the same thing. It broadcasts its tag, which is B. B goes everywhere, and it broadcasts its value also. So every location that's waiting for B, let me go back. That's waiting for B, and that's invalid, captures the value that's broadcast, and essentially they get 8. And now they can execute, right? And the third slide is basically other stuff happens in the same cycle. Okay, I think this is probably a good place to stop. You can do I would suggest that you do the animation on your own and go through this later today. We're going to continue from here. I'll see you tomorrow.